Have you ever wondered how your computer recognizes patterns and makes decisions? Well, in the realm of computer science and theoretical research, a fascinating device called a finite automaton plays a crucial role. Imagine it as a mathematical abstraction of a simple computing device, operating on an input string of symbols, each plucked from a finite alphabet. It transitions through a finite number of states, following a set of predefined rules. Now, what's the magic behind this process? It lies in the ability of finite automata to recognize patterns within strings and solve various decision problems. Think of it as a detective, deciphering coded messages and making decisions based on the clues it uncovers. Let's break down the key components of a finite automaton. The alphabet, denoted by sigma, is a finite set of symbols forming the input string. Think of it as the language the automaton understands. The states, represented by Q, are the different conditions the automaton can be in at any given time. The transition function is a bit like a map, guiding the automaton from one state to another based on the current state and the input symbol it reads. The initial state is where the automaton starts its journey, while the accepting states are the successful endpoints, indicating the recognition of a certain pattern or condition. The automaton reads the input string, a finite sequence of symbols from the alphabet, symbol by symbol. It transitions between states according to the transition function, operating in discrete steps. It halts when it reaches the end of the input string, or when there are no more transitions possible. At that point, it either accepts or rejects the input string based on whether it has reached an accepting state. Finite automata come in various forms, like deterministic finite automata and non-deterministic finite automata, each with its unique characteristics and capabilities. They are the unsung heroes in the study of formal languages, and regular expressions. So let's dive deeper into the key components of a finite automaton. First up, we have the alphabet. Don't worry, we're not going back to preschool. In the realm of finite automata, an alphabet is a finite set of symbols that forms the input string. It's like the vocabulary of a language. Just as words are made up of letters from an alphabet, the input string for a finite automaton is composed of symbols from its alphabet. For example, let's consider a simple finite automaton where the alphabet is denoted by sigma and consists of just two symbols, 0 and 1. So sigma equals 0, 1. This means that any input string for this automaton can only contain the symbols 0 and 1. It could be a string like 0, 1, 1, 0 or 1, 1, 1 and so on. The alphabet is crucial as it sets the groundwork for what the finite automaton can process. Now that we know what the alphabet is, let's move on to the states. Next, we have the states. Now, the states of a finite automaton aren't geographical locations. Rather, they represent the different conditions or configurations the automaton can be in at any given moment. Think of them as the different moods of a person, each mood leading to distinct reactions based on the situation, or in this case, the input symbol. This finite set of states is denoted by the letter Q. And just like a person can only be in one mood at a time, the automaton can only be in one state at a time. Each state is unique and plays a specific role in the functioning of the automaton. It's this interplay between states, driven by input symbols, that gives finite automata their power in pattern recognition and decision-making. So in essence, the states are the heart of a finite automaton, pumping life into its operations. With the states understood, let's explore the transition function. The third component is the transition function. This vital piece of the puzzle is the rule set that determines how our automaton transitions from one state to another. It's like the navigator of an automaton's journey, guiding it through the landscape of states based on the symbols it encounters in the input string. The transition function is formally defined as a function mapping from the cross product of states and alphabet symbols to states. In simpler terms, given a state and an input symbol, it specifies the next state our automaton should transition to. Imagine the automaton as a chess player, and the transition function as the chess rules. The player is in a state, say contemplating a move, and the input symbol is the move they're considering. The transition function, acting as the chess rules, then tells the player what state to transition to, such as moving a piece or declaring a checkmate. Transition function covered, let's look at the initial state. We have two special types of states, the initial state and the accepting states. Dive into the world of finite automata, and you'll find these two states playing pivotal roles. The initial state, denoted as Qt, is where the journey of computation begins. It's the starting point of the automaton's operation, the origin from which it embarks on its quest of processing the input string. Picture it as the doorway to an intricate labyrinth. It's the first step into the maze, the foundation from which the automaton navigates its path through the complex network of states, guided by the transition function. On the other hand, we have the accepting states. These are not just any states, they're the ones that signify success. They're the states that indicate the automaton has successfully recognized a pattern or condition in the input string. If the automaton ends up in any of these states after processing the input string, it's a win. The string is accepted as part of the automaton's language. Think of these accepting states as the treasure chests hidden within the labyrinth. If the automaton can find its way to one of these chests, then it has successfully navigated the maze. It's in these states that the automaton declares, "I've found what I'm looking for." But what is this input string that we keep mentioning? Well, it's the sequence of symbols from the alphabet that serves as the automaton's guide. It's the map that directs the automaton through the labyrinth of states. The automaton reads the input, symbol by symbol, transitioning between states according to the transition function, seeking out the accepting states. In the grand scheme of finite automata, the initial state is the starting point, the accepting states are the goal, and the input string is the route. Together, they shape the automaton's journey from start to finish. Recognizing the importance of initial and accepting states, let's discuss how a finite automaton operates. So, how does a finite automaton work? A finite automaton operates in distinct, discrete steps, much like the ticking of a clock or the steps in a dance. Each tick, each step corresponds to the automaton processing an input symbol from the input string. As it reads the symbol, it moves from its current state to another state, guided by the rules set out in the transition function. Imagine the automaton as a hiker navigating a map. The current state is where the hiker stands. The input symbol is the path they choose, and the transition function is the map directing them to their next location or state. The hiker keeps moving, processing paths until they've traversed all the paths or there are no more paths to tread. This is the halting condition of the automaton, the point where it stops its operation. At this juncture, the automaton makes a decision to accept or reject the input string. If our hiker has ended up at a location marked as an accepting state, the automaton accepts the input string. It signifies that the automaton has successfully recognized a pattern or condition. If not, the input string is rejected. So, in essence, a finite automaton is a pattern recognizer, operating in systematic steps, making decisions based on where it ends up in its state journey. Now that we understand the operation, let's briefly touch on the types of finite automata. Finite automata come in various forms. Two of the most common types you'll encounter are deterministic finite automata, or DFA, and non-deterministic finite automata, or NFA. Let's start with deterministic finite automata. In a DFA, for every state and every input symbol, there's a single unique transition to another state. This means the DFA's next state is strictly determined by its current state and the input symbol. There's no room for ambiguity or multiple possible outcomes. On the other hand, non-deterministic finite automata are a bit more flexible. In an NFA, for the same state and input symbol, there can be several possible next states. This introduces a level of uncertainty, as the NFA can potentially transition to any one of these states. Both DFAs and NFAs have their own characteristics and capabilities. DFAs are easy to implement and their behavior is predictable, while NFAs provide greater expressive power and flexibility. These types of finite automata play a pivotal role in the study of formal languages, and regular expressions. They help us understand and model computational processes, pattern recognition, and decision-making problems, making them a fundamental concept in theoretical computer science. So there you have it, a comprehensive understanding of finite automata and their role in computer science.